Okay, good morning and welcome to today's lecture about dimensionality reduction and how we can do it, what we can gain from it, and what we need to take care of. Okay, so this is our agenda. We will first introduce the problem, then talk about the PCA, and then we will see how we can use the PCA in applications, and we will talk some more about data preprocessing. So we already seen some preprocessing steps during the last exercises, and today we will talk a bit more about it. Okay. Okay, so when we work with high-dimensional data, for example, images, this process has some difficulties. So first of all, it's hard to analyze, and the interpretation is also quite difficult. Visualization is almost impossible, and so the more high-dimensional our data gets, the more computationally expensive the whole process becomes, and also it's getting more memory. Needs more memory to store the data if we have more dimensions. So for example, this data set, so this is just a part of the data set where we had 53 blood and urine measurements from 65 people. And so you see there are only 9 of those and only 7 columns. But so this is how such data set look like. And how would you visualize stuff like this? So in this case, we have 7 columns. And imagine you would have 53, even more. So first we can say, okay, we will maybe prefer univariate visualization. So like take one of those features and visualize it individually, or we can choose bivariate visualization and visualize some 2 features against each other, or we can maybe go even as high as a 3-variate and visualize 3 features against each other, but basically this is where we stop because everything else is hard to visualize. But what about, so you saw we only could do 3 axes, and it's not a good idea, or at least we don't gain much information from that sometimes. And the question is there a better data representation than those ordinate axes? So those basically are the usual axes in the coordinate system. And we want to ask ourselves, is there a better data representation than that? Do we actually need a 53-dimensional space to view the whole data? Because, how could we manage to do this? And what we ideally would like to have is to find the best low-dimensional space that conveys maximum useful information. So not just project our data into any low-dimensional space, but find the best one. That's why we basically need dimensionality reduction, or this is one of the reasons. And the good thing about high-dimensional data is that it often comes with properties that we can exploit. So even if it has high dimension and has these bad things or not convenient things for us as high storage, high memory, high computational times, but there are also some pluses about high-dimensional data. And this is, for example, it's often overcomplete. That means many dimensions are redundant and can be explained by a combination of other dimensions, for example. Or dimensions are also often correlated so that the data possesses an intrinsic low-dimensional structure. So even if we have this high-dimensional data, the intrinsic dimensional structure is low. So, for example, for images, this is often the case, or 3D scans. And dimensionality reduction exploits this structure and correlation and allows us to work with a more compact representation of data. And ideally, we want to do this without losing any information, or if we lose some information, it should be only a small amount, or even it would be the most preferable way if we lose the only noise information. Yeah, so dimensionality reduction can be viewed sometimes as a compression technique, or often that way. Okay, so for example, how we would manage high-dimensional data. Here we have this set of scans, database of phase scans. Each scan has 3D geometry and texture, and there are 10,000 points in each scan. So basically we have X, Y, Z coordinates, and we have this RGB values for each point. And that means that each scan is basically 60,000 dimensional vector, which is very high, and this is really inconvenient to work with this. But good news is just what we said right now. Phases are likely to be governed by only a small set of parameters, much less than 60,000. And also this goes for images, not only for 3D scans. And here where the PCA goes. So our goal, as we said, is to find the best low-dimensional space that conveys the maximum useful information by looking for principal components. So I mean, the goal was the first one, but by looking for principal components is the idea how we will do this. So we will try to find the best low-dimensional space that conveys the maximum useful information. And that means we need to think about which components or which features are important to keep. And what we maybe need to think about more, so when we have our features and they vary a lot, so through the feature, through all the examples that we have a feature that has high variance, that like varies a lot. That probably mean that we need to keep it because there is a lot of information stored in there. But there is if there is a feature that almost always stays the same or varies only a little bit, then maybe it's not useful. Maybe we can just throw it away. So that means in our case, we will define the importance of a feature or significance of the feature by its variance. So the higher the variance of the feature throughout all examples, the more important this feature should be, and the more probable is that we should keep it. And artificial intelligence, in this case, would be recognizing this significance or this importance. So it should basically throw away the features that we don't need or they don't give us much information and keep the features that are important. And the retaining most information after data compression is, in this case, equivalent to capturing the largest amount of variance. So if after some transformation in a lower dimensional space, we manage to capture the most amount of information, ideally all amount of variance, then we basically didn't lose any information. And that would be our goal. So basically, we now have a source to measure information amount, and this is variance. Okay? So since we have several features, we are not talking about variance. Actually, we're talking about covariance. And how we see our data here. So we don't have any labels. We have just m-dimensional vectors. And each such example has m features. Okay? And the data would look like this. So our data, this is basically what we used to. This is our basically matrix, and we have m features here, and we have n examples here. This is what we used to. So sometimes, if you look at the literature, then they say for exact this problem, so in order to compute PCA, we for once, so this is the usual representations when you go in through examples. You have here always number of examples, here number of features. And for And in some literature, you will find that for this special case of the computing of PCA, they would switch it for once. They would say, okay, even though it's not convenient, it's not how we usually represent it, we will put the features here, the feature dimension here, and the example dimension here. And then, because this is more convenient with the definition of the covariance, but I still thought it would be best if we keep it that way, and I adjusted the formulas that we will use today to actually implement the PCA accordingly, so that you can just use the formulas, and then you will compute everything correctly, and having in mind this representation. So we have our rows of examples and the columns of features. Okay, so we basically combine this example is in n times m matrix. So through the whole part of today, these dimensions are important to keep in mind. And the covariance matrix, so usually the covariance matrix of such matrix would, one thing which is important. We need to subtract the mean. I'll first tell you why it's okay to do it, and then we'll see why it's nicer to do it. So if we have some data, I don't know, here we have points, right? And this is our coordinate system, and this is 0, so this is not zero mean. If we shift the whole data to the mean, to the zero mean, it won't change the variance. You agree with that? So it doesn't mean if we shift the data, so whatever will shift the data, as long as we don't scale it, if we just shifted it, the variance wouldn't change. Is it clear? So that's very convenient for us, because that way, since the variance between a feature, throughout the features doesn't change, we can conveniently say, okay, we shift our data to have zero mean, basically transform it as a first step like this, and it will still have the same variance. And why? So this is why we can do it, but why is it convenient to do this? The convenient is just because, so your usual variance formula or covariance formula says that if you compute the covariance between two variables, then you would basically calculate the, okay, never mind, calculate the expectation value of the product, and then you would subtract the expectation value of each of those, of the means. So basically, this is the mean, the expectation value of each of those. And if we say that our means should be 0, then we can get rid of this part and continue only with this. So this is only for convenience, because otherwise our computations will be longer than they should be. And since we don't care about the mean, we only care about the variance, we can just say we get rid of our mean, and that's why we don't need these additional computations. We only can basically represent our covariance like this. Okay? And this, so usually you would say the covariance of a matrix on itself, so here we had two different, but on itself would be calculated as like this. But as I said, if we would do this, then it wouldn't be convenient for us, because then we will calculate the covariance of examples on the examples. And that's why I said I changed this dimension. I transposed it basically internally and say I want to have the covariances between the features. So this is what the matrix should look like. It should be D times D. And in order to achieve that, I need to compute this value. So what our covariance matrix looks like, it has D times D features, and for each features, so this will have our variances of each feature of themselves, and on this we will have these covariances. Okay, and the good thing about this covariance matrix is that it has properties. It's positive semi-definite and symmetric. And these are very convenient properties for us. And we can exploit them. So we are sure whenever we compute a covariance matrix, it will definitely be symmetric and have full rank. And now, now we can exploit this. But first, let's just briefly get the idea what covariance actually describes. So in the first case, it says, okay, here you see, the feature x is not dependent on the feature y, because and that means in the matrix. So if you look at the matrix, you would see this independence if you see zeros between the features. So if you see on all those diagonals, which are not variant, so this is our variance diagonal, and on all those other places where there are no, where there is no diagonal, if there are zeros, then between those two there are no, so they are independent. This is what it looks like, and in this case they are dependent, and this is how it looks like. So if you have something like this, or in other ways, so if it would be plus here, it would look the other way around, like this, it would have. And that would mean that x and y is not independent. So if we have such data, and usually they are dependent somehow. And that's why we could exploit it, because we already have this dependence, and and that means we have redundancy. Okay, so this is basically what our covariance matrix would tell us if it would look like that. So if we had something like that, then we have independence between our features, and if we have something like this, so those are not zero, then the features are dependent. And now you see how this symmetrical, so it's always symmetric, okay? And yeah, basically, so what this says that is if one feature increases, then the other decreases. Okay, yes, and what we want to achieve with this principal component is we want to find an orthonormal matrix P as a basis transform for our, so this is X is our matrix, and we would like to find such transformation P such that the resulting matrix will have the covariance, basically the covariance matrix should be diagonal. That means all the other elements between each features should be not correlated. So we will, if we could achieve that, that means we would remove the correlation between the dimensions, and everything would look like this. So all the features would be independent. So basically, our goal is to remove this dependence between the features. And for that, we will need to search for such this orthonormal matrix as a basis transform. And with these characteristics, so first of all, this transform should allow us for the resultant covariance matrix to be diagonal. And the second, in this matrix, the dimensions should be ordered by importance. So the first important dimension should be the zeroth coordinate, and the second, and so on. So decrease in order of variance. Okay, and then if we could achieve that, then the columns of P would be our principal components of X. And this is basically what that says here. We had our ordinate axes x1 and x2, and we transformed this whole thing in another coordinate system where we have now this axis, y1 and y2. And as you see here, they are orthogonal, so that means the angle between them is 90 degrees. And that means that the correlations are removed. So basically, here we have 2 dimensions. Oh, sorry. So here we have 2 dimensions, and in the case of 3 dimensions, the third y would be also orthogonal to both. So each of the vectors of each of the components in this y matrix is orthogonal to all others. So they are all orthogonal to each other. This is the important part. So here you see these both are orthogonal, and if it would be the third, it would look like go straight through and be orthogonal to both. So this is basically the idea, and that way you see already if we do this, then our first component would capture the most variance, so it will lie where we have the most variance, and our second component will lie on the axis where we have the second most amount of variance. Okay. Yes, and there are some rules which we can use in order to find this transformation P. It can be shown that the principal components of a data matrix X are the eigenvectors of its covariance matrix. And if a matrix, so this is first thing which we need to explore, and the second thing, if some matrix, no matter which matrix, is symmetric, then there is always an orthogonal eigenbasis. So you remember when we were talking about last time, we said, so if the matrix, so we don't always have eigenvalue decomposition for each arbitrary matrix. Sometimes there is not. But if the matrix is symmetric, there is always one. You can always find orthogonal eigenbases. By the way, the orthogonal, so the difference between orthogonal and orthonormal is that, basically, orthogonal means that only the dot product between them is equals to 0. So they are all of those are perpendicular to each other, and orthonormal means that the length of each component is equal to 1. So you can also, so basically, yeah, so they have unit length. Okay, and yes, this can be shown, and we can exploit this, that because we say, okay, since we have this covariance matrix, and we are sure that covariance matrix is always symmetric, and if the matrix is symmetric, then there is always an orthogonal eigenbasis. That means we will perform eigendecomposition of our covariance matrix. And this is how it would look like. So imagine our A is not our original X, but our covariance matrix. This is how this decomposition looks like. So here we have our eigenvectors as columns. Here we have eigenvalues on a diagonal, and here we have transposed eigenvectors. And then we will just need to take this as a basis. And basically, we will be done. And this is the algorithm to perform PCA for dimensionality reduction. First, you need to center your data by shifting data points to have 0 mean. So this, in order for us to have these calculations easier. Then, second, you would compute the covariance matrix. So basically, the second step is to project data to eigenspace, but there are several steps within this projection. So first, we will compute the covariance matrix of the centered data. Then we will find eigenvalues and eigenvectors of this covariance matrix. Then we will sort our eigenvectors according to eigenvalues. So if we will look at our eigenvalues, we will see that the most important eigenvectors will have the most higher eigenvalues, and then we will sort eigenvalues and eigenvectors according to eigenvalues. Basically, we don't need eigenvalues after that, so eigenvalues are only needed for sorting eigenvectors because our principal components are actually eigenvectors. So eigenvalues you will only need in order to basically see which vectors are most important and put it in the first place, and so on and so on. And then this is the projection of our data to eigenspace. Then we're done. And then afterwards, when we project it, we say, okay, we neglect those dimensions or those eigenvectors which have small eigenvalues. Like neglect means that we just don't take them into account. Okay, so this is really similar to what we did last time, but now we can use eigenvectors for that. We don't need a singular value decomposition. It's Yeah, it's more convenient. And then that means that eigenvectors that correspond to large eigenvalues are the directions in which data has strong components. So, if you this representation earlier, we had this data, and we found this new representation. And this new representation shows you actually the direction where it has higher variance, here and here. Okay? Is that clear? It's actually not so hard, but it's very effective. Yeah, so this is basically the algorithm which you need. Yeah?
Can you go back to one slide?
Yeah?
Oh, yeah, that one. So the green matrices are like the transformation matrices, right?
Can you speak a bit louder? Sorry.
The green matrices are like for the transformation.
The green, yeah. So the green matrices are the eigenvectors, which we will take afterwards.
Don't usually, so these are just like transposed, but isn't it usually that we have to invert one of them of the unitary series?
For what would you like to invert them?
Well, I thought basically you're transforming, then multiplying the lambdas, and then transforming back. And to transform back, you have to invert the first transforming matrix, not just transpose it.
I think you're confusing with this singular value decomposition, this procedure. So this is really similar and it's connected to that, but it's not the same. So this is actually the eigenvalue decomposition. It's similar. It has similar ideas, but this is not so universal. So a singular value you can perform on each matrix, no matter which dimensions, and no matter if it's symmetric or not. And eigenvalue decomposition is a little bit special. You can only do it on some particular matrices. And for example, a symmetric matrix we can do it. So that's why today we really use the eigenvalue decomposition, not the singular value decomposition. But they are connected because basically the singular values are the squares of the eigenvalues. So we could also do that. So what was your question?
So I just want to say that because it's symmetric, then the transformation matrices are unitary, and for a unitary matrix, the transpose is also the inverse.
Yes. Okay. Yes. That's if it's on the issue, yeah. Yeah, that's true. Okay. So basically, you can use SVD also for PCA. It's actually what I think is behind the solver in sklearn. But when you implement it yourself, you usually actually calculate the eigenvalue. But there are both ways actually to do this. Oh, sorry, I'm here already. Okay. Where was I? Here. Yeah. Okay, so those are the steps, and I think I'll write you the formulas for that when I'm showing an example maybe. So this is the algorithm which you need to implement today, or at least part of this. And what can we do after we reduce the dimensionality? So we here, you see, we have these neglected dimensions, and now we, for example, can use it for data compression to store only k largest eigenvector in the mean vector. So if you just want to compress your data somehow, then it was large and had many dimensions, and in order to really store it as compressed data, you only need to store k largest eigenvalues and the mean vector. Or you can first store all eigenvalues and then the mean vector in order for the people afterwards to choose which largest, which k they need, but then you wouldn't really compress much. So for compression, you would find such k, which is convenient for you, and then store only the top k eigenvectors and the mean vector. You always need to keep your mean vector running because Otherwise, you wouldn't be able to transform your data back into your space. For pre-processing, then you could do two different things. You can either take your principal components and operate on them. So you will say, okay, I have only K components, they are important, and then I can, for example, cluster on those components or perform training on those components. Or you can project back first. So take top largest eigenvectors, project back, and use this pre-processed lower dimensional data set for further operations. So it's your choice, whatever is convenient, whether you really start to do your operation on principal components, then you, of course, still need to project your data back afterwards, but, or if you perform a classification, for example, then you will just need to have the results, so you don't have to project the data back. But if you want to restore the data, you would. So either you operate on principal component as features, so just say, okay, I don't care about my features which I had, I will take my new features, which are principal component, or you first project back and use this new lower dimensional data set for further operations. Or, for example, for clustering, it's convenient to do this. So clustering usually gets better if you first, or faster, if you use these transformations forward and backward. Or denoising, it's can be used for denoising. In that case, you would transform back because you will need to see basically the denoised data. Because you would think then that your eigenvalues with eigenvectors which have low eigenvalues, they correspond to maybe noise. That's why if you reduce them, you maybe reduce noise. Or trading. You just basically, as I said, either train on your principal component as features, or you transform back and train on smaller dimension. And yeah, there are some other applications which you can do afterwards. And if you use PCA or dimensionality reduction for visualization, then you would usually take first 2 to 3 components, 2 to 3 components to visualize your data. So you can say, okay, my first component and my second component have the largest variance, largest captured variance, and I use on the DOM to plot my 2D data, to project my 2D data, or you can take the third one and visualize it in 3D. So there's this possibility. And this is an example, and then I should probably write the computations which you need to perform today. So first, here is this original data set, which lies somewhere here. And you see there are correlations. Okay, sorry, you don't see it here, but no matter. So the first step is always centering. Although I must say, I sometimes try to perform my PCA without centering data, and the result changed, but not so much. But still, it's better to first center the data. Then sometimes, so this step is optional. Sometimes it's convenient to divide by standard deviation to make the data unit free. But so this step, so you don't need to implement it today. And the second is you will compute the eigenvalues and the eigenvectors. So you will say, okay, this is my matrix now, and I will calculate the covariance of this data matrix, and then compute my eigenvalues and eigenvalues. So you use the eigenvalue decomposition in order to get those eigenvectors. And in this case, as you see, they don't have unit variance. They are multiplied by the eigenvectors, eigenvalues. So here it's just for convenience. So usually you would like have here eigenvectors have unit variance, but in order to show they basically, so this will be the eigenvector multiplied by eigenvalue, so that you can see, until where it goes. And those are your principal components, these green lines. And then the next step would be the projecting data on this subspace. So as you see, this data gets, so this is maybe not so clear. So this is the black line, but actually the data starts here and ends here. So basically what it's done is I say this is my line which I want to project, and I project it orthogonally. So like put this vector, this point onto this axis, and put here, and put here, and put here, and put here. So basically I approximate my data only on one, to be on one axis. And this is how it looks like. So here I'm projecting my data onto this principal subspace, and now it's one-dimensional instead of two. So here we were two-dimensional, now we only have a line. Okay, and so this is the project part. So this would be basically corresponds to these computations, what you need to produce here, so project. You have your, you'll get your reduced matrix by taking your centered matrix. So imagine we already centered this data, and multiply, perform matrix multiplication with this selected k eigenvalues. So those are the selected k, sorry, not eigenvalues, eigenvectors. Vectors. Okay, so this will have the dimensions of the size n times k. This had our original dimension n times m, and this dimension would be m times k. Okay, so we'll select k columns, and then we basically multiply with this matrix, and then we'll get our reduced. So this is the project step, this one.
Okay, sorry. X is not the variance matrix, but the vector itself.
Yeah, this matrix. Or so x-centered would be this matrix with subtracted mean. Okay, and this would be the step back. So if you need, so sometimes you can just use this and do your operations here. But if you need, you can project back, and you will also project back today. And how you would do it? So basically, you let me maybe. I think I can write it here. Okay, project back. Would be just, so now you have this x reduced, and you still have your selected eigenvectors, and you get your x reconstructed by basically taking this one, reduced, and multiplied by this v transposed. And this v, so this is the same, selected k eigenvectors. Okay, so your dimensionality would be, so here you will get back to the original dimensionality. This is our dimensionality here, n times k. And this is the transposed, that means k times m. So this is what you will need to do. So those are the steps. And then you are here. Sorry, forgot one important thing. Of course, this is not finished. What's missing here? So what is missing here? If we project back to our space? Sorry? What? Yeah, so the mean. Yeah, so we need to say plus mean. Yeah, this is important because otherwise you wouldn't get. So for example, if you do this on an image, you will get shifted images which won't look so nice. So don't forget. So that's why we need to always carry on the mean afterwards, because otherwise we won't be able to. So basically what we need in order to project back, we will need all three things. We will need to carry our eigenvectors, we will need this reduced data, and we will always need the mean. And then we can reconstruct. Otherwise, if something's missing, then we cannot construct. Okay. So this is Okay, so this is basically what we are here. Afterwards, in this lower dimensional space. So as you see, we still have basically 2 dimensions. So we still need to express our points in 2D, right? But the dimension of the actual point is 1, and it's lower, so in comparison to this. Okay, so here we needed basically 2 axes to express our data, and here we have only 1 axis, and this is this dimensionality reduction. We have only 1 feature instead of 2. Okay. Okay, and now how we can use it? So first, as I said, approximation. If you project it, so these are these eigenvectors. If you basically project your points orthogonally on this space, you will get such data, which is approximation of your original set. And sometimes it's not a bad approximation. Sometimes you think, oh, okay, maybe this is just noisy points, and actually it's a line, and there are some noisy observations. So this would remove this noise if it would be noise. Okay. And the thing is, of course, you can, if you had such data, you can choose to project on any axis. So why would we need to actually compute the principal component first and then project it on the highest principal component instead of just, I don't know, doing the line here and project it on there? And it's been shown that this approximation of the projection onto the highest eigenvalues is optimal in the least square sense. So you can possibly find another axis so you cannot possibly find another axis on which you can project those points and get better approximation. Every other approximation would be worse. So here it would be like an example on arbitrary line. So you see we lost more information than here. So here almost all information was retained, and here not. So this has been proven that approximation on the principal components is the best in the least squared sense. And there's another application which is maybe you're not familiar. So when we want to calculate a collision of 2 objects, we can use a tight bounding box in order to fast. So usually if you will try to do collision detection, you would need to go through a lot of points and calculate whether they collide. And if you want to, so often we don't really care about the actual points. We just need to see will they roughly collide or not. So this is a very convenient way. We just say we will first compute the bounding box, which is as tight as possible, so that we don't stretch it too much. So that's why in order for our collision detection to be as accurate as possible. And then you would just see if the bounding boxes overlap. And this is much easier to check instead of going through the objects and see if they are overlapping. So in this case, bounding boxes serve is a very simple approximation of the object, and used as a fast collision detection. And of course, if we would need to use this, it here, then the tighter the bounding box, the better. And how can you find the tight bounding box? So if you will take just axis-aligned bounding box, which is often taken, but not in this case, so you can calculate axis-aligned bounding box, but it would be not optimal bounding box for the collision, because as you see, we have here the space, which is like not an object or not in points, and this is kind of a waste. And how can we calculate it better? We can compute the bounding box with respect to not the ordinate axis or our original axis, but we will take axis aligned, but with respect to our eigenvector axis. So we first project, and then we will put the origin in the mean point, and then we will basically calculate the bounding box with respect to axis not that we have in our first space, but in this transformation defined by eigenvectors. And then we will have the optimal bounding box. And then we can perform fast collision detection. And so we already talked about this preprocessing a lot, but let's review. So usually or often we need to preprocess the data before we do something with it, whether it's training or clustering or something like that. And what we already know is the standardization. So we subtract by the mean and divide by the standard deviation such that we have 0 mean and unit standard deviation afterwards. And this is done where? In such operations where you use algorithms which internally assume your data to be standardized. So for example, SVM or some linear regression things or clustering, as we saw yesterday, so it would already sometimes, so often in the libraries already assume that your data is standardized and wouldn't perform this operation within. So you remember we needed to first scale and afterwards calculate our SVM because it wouldn't do it for us. So many predictors which we use require us to do this, especially if you are working with distances. Random forests, you would need to do this, you know, but you're not always performing random forest. And why we would need to do it here is because if a feature has a variance that is orders of magnitudes larger than others, then it might dominate our objective function, so our distance function, and make the estimator unable to learn from other features, but only learn from this one. So that's why this unit variance is important. And the second preprocessing of data, which we haven't done before, which we'll try today, would be the dimensionality reduction. So you would not only make the standardization, but often you can do dimensionality reduction as a preprocessing. And in order to do this, you need to be careful because all kinds of preprocessing should be performed only on trained data. You're not supposed to look at your test data because then you will get information about the mean and variance and stuff like that. That's why any type of preprocessing always has to be performed on trained data. And after you do this, after you finish the training, the transformation information, so everything that you needed in order to perform the first transformation as preprocessing, you need to carry on together with the model to the tester. So you not only release your model, but for the person who will be testing your model or using your model, you will also need to release all the information that you used for preprocessing. And this is, for example, how it's done for neural networks. You usually, if you use some model, I don't know, ResNet, you will see it afterwards. You don't have only a model, but you have information for transformation. So you first need to transform your data accordingly and then use it. This is really important because otherwise your model will perform operations on transformed data. So it wants to perform the operations on transformed data, but if your data is not transformed, then you will have the so-called domain gap. So you will be dealing with other domain, and you won't get good results. So that's why it's really important to give the tester all the information that you have. So for example, in here, you would need to carry the mean. You would need to carry all the eigenvectors that you used. So basically, the reduced would be the model, so you would need to give it away anyway, but this information is important too, because otherwise you wouldn't be able to reconstruct this information out of this without this data. And in the case of standardization, you would need to carry on the mean and the standard deviation, both two. Yeah, so depending on which preprocessing you use, there's transformation. And before testing, you always need to first preprocess your data on the same way and then test. And what will it lead? So usually, so basically always, definitely it's guaranteed to converge faster. So if you preprocess your data, usually it will at least give you the possibility to converge faster, and sometimes you will even get better results. And of course, you need to be to keep in mind that some transformations, some preprocessing is not suitable in some things. So it's not basically a uniform thing to always perform PCA on your data, because some data cannot be so some data is not good for PCA, because basically what PCA does is it performs linear transformations. So it's not that you can really say always perform PCA before you do something, or always perform standardization before you do something. So it's not the case. You need to be careful sometimes, but it's often the case. And as I said, the first result which you usually will get is faster convergence. And sometimes you will even improve the results, as we will see today in the exercise. Okay, so any questions? Because I think I'm done. Okay, then.